Hey kids, it's Charlie Abuso, and guess what? We're back for the last slideshow, the last Zoom for trends on the periodic table. This one's going to be a little longer because I didn't want to make two short ones. Here we go. We did the group trend for first ionization energy in the last Zoom. First ionization energy is the amount of energy required to turn a mole of atoms into a mole of positive one, or what they call first order cations. That's why it's called first ionization energy. There is also a second, third, fourth, etc. If you have to pull off more electrons, for instance, magnesium, or here, strontium is the second element. Strontium doesn't become a positive one ion, neither does yttrium. The state only gives us the first ionization energy. This is about reading a chart, understanding the numbers going up or down, being lazy or not being lazy. It's pretty easy, but most atoms don't make positive one ions. The nonmetals don't either. The noble gases never want to make ions, but you can make it happen. It just takes a lot of energy. Here we go. Looking at table S. What are the numbers? And what is the trend? And you have to say it as simple as possible. So here we go. Ba-boom. The numbers come right off of table S, and it's obvious that when you go across the period, these numbers are increasing. And if you look at any period, I happen to pick this one, but any period, the numbers will increase. And how do you say that? How do you say that? You say it like this. The period trend for first ionization energy is increasing. Which direction? This period. What trend? First ionization energy. And what are the numbers doing? They're getting bigger. The reason for this is when you go across a period, you have the same number of electron orbitals. Now, every atom you go across, you are adding electrons, but you're adding them to the same number of orbitals. You're also adding an extra proton to the nucleus. So the nucleus gets more and more positive. As you go across the table, you get more and more and more protons with the same number of orbitals. And yeah, there are more electrons, but they're in the same number of orbitals. So the inward attraction, the positive pulling on those electrons, pulls tighter and tighter and tighter. So going across the table, the smallest atoms tend to be the noble gases, and it gets harder and harder to pull those electrons off. That's what this means. When you're on the left side of the table and you have 4 orbitals, right? You have a certain number of protons, but as you go across, you get more and more protons with 4 orbitals. You get a greater and greater inward attraction. You make it harder and harder to pull these electrons off. Now, this may be one of the stupidest things I have to teach you. The whole periodic table is made up of nonmetals or metals. Now, there are 7 metalloids, but they're metals or nonmetals also. They're just also called metalloids. They have some crossover type properties. So let's look at some of these properties. You need to know these properties. Most of them are pretty obvious. Jot them down. Now, to be a metal, metals, when you bang them, they get flatter. They don't crack. They're called being malleable. They can also be called ductile. That means you can string them out into the shape of a wire. You pull them and they stretch, sort of. They don't crack. They have the ability to conduct heat and electricity. Frying pans, wires, they're made of metals. They form into cations because metals lose electrons to become isoelectric to noble gas to bond. They tend to be shiny. They have luster, right? They're reflective. My gold wedding band, you see it, right? Even in this little picture, you can see it. You know why? Because the light's shining off of it. It's lustrous. They have a low specific heat capacity constant. That means they change temperature really quick. They heat up really quick. Remember, water, which is a nonmetal, is 4.18 joules per gram dot Kelvin. Gold, I think, is 0.14. 0.14. Copper is 0.39 compared to 4.18. So these are some metal properties. Now, nonmetals are not malleable or ductile. They're actually brittle. A lot of the nonmetals are gases that, bromine's a liquid. They're not actually solid, but the ones that are solid are brittle. When you hit them, they crack. They don't conduct heat or electricity, and they form anions. Now, the noble gases, which are also nonmetals, they don't form any ions at all. They aren't lustrous. Almost all nonmetals are pretty dull, blah looking, or they're gases, and it doesn't apply. They tend to be less dense than metals, and they tend to have a higher specific heat capacity constant. than metals. So there's a difference between the atoms, and a lot of those differences are really because of the way they bond or because of the way their electron orbitals are built. But the properties of metals are in like one group, and the properties in metals are in another group. And there's a few elements, metalloids, that have sort of some crossover properties. They're right on that staircase line. They are metals or they are non-metals, but they have some crossover properties. Now, if you could rank all the metals for all the properties, which is the shiniest metal, which is the most malleable, which makes the cations the easiest, which is the most ductile, which has the lowest specific heat capacity constant, as it turns out, as a general rule, the most metallic element is francium, which is on the bottom left corner of the periodic table. It's way down here. And if you measured all the non-metallic properties, which is least likely to form a cation, which conducts heat the worst, which conducts electricity the worst, I don't even know what that means, it probably just doesn't. But if you could list all of the non-metal properties and rank which atoms are the best at this and took an average, helium. So you got francium in one corner and helium in the other corner. This is generally true. There's always exceptions. Some atoms are actually more metallic in one ranking than others. But overall, francium is the most metallic. Helium is the most non-metallic. You just point like this, right? You point like this. Two corners of the periodic table. Now, this is really kind of crazy. Let me see if I can move my picture out of the way so I can see it. Of the yellow ones through the middle, boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Those are metalloids. Now, Ge and Sb, germanium and antimony, those are metals. They're metals, but they have some non-metallic properties. Like if you bang on them with a hammer, they crack. Now, on the other side, the other five yellow ones, boron, silicon, arsenic, tellurium, and astatine, they are non-metals. But for instance, silicon, it's very lustrous, and it does conduct electricity. We make computer chips out of it, but that's weird, right? It is brittle. It doesn't form cations. I mean, it's a non-metal, but it has some metallic properties. All right, so those are the metalloids. Now, we pointed out the most metallic francium in one corner and the most non-metallic helium in the other corner. Now, this is dopey. Oh, I can't talk to my best friend. I'm telling him I can't talk. Can I talk to you later? Which element is the most metallic of these? Strontium, which is over on the left, copper in the middle, or lead? Now, how do we figure this answer out? Which of these three boxes, strontium, copper, or lead, which box is closest, physically closest on the table using a ruler in inches, which is closest to francium? Well, strontium is clearly much closer to francium than the other. This general trend, which metal is the most metallic? Strontium is the most metallic because it's closest to francium. So how do you decide which is more metallic than another? Literally, which box is closest to francium? This is stupid, dopey, but it is. I mean, come on. Now, here's another question. Which of these three elements is most non-metallic? Neon, sulfur, or bromine? Now, neon's a non-metal, sulfur's a non-metal, bromine's a non-metal. But if you had to pick right now, pick which one is the most non-metallic, literally, which of these boxes is the closest box to helium? And you can't even draw a line. It's touching. Neon is obviously closest. So neon is therefore the most non-metallic of them all. This is pretty dumb. Okay. You know what's really cool about this table? I have to point this out. Look on the left side in the third groups, scandium, yttrium, Sc and Y. Then there's those two white boxes with the stars. Look how this table is set up compared to our table. We have scandium and yttrium. Get this out and look at this, please, right now. Scandium is in group 3. Yttrium is in group 3. La and Ac, lanthanum and actinium, are also in group 3. And then we have this stupid black line that's very confusing. Look how well set up this table is. On the very bottom, those inner transitionals, with the first star, Lu, luteum, all the way out to Yb, erbium. All those elements in a straight line across the bottom, they all fit into that box with one star. All of those blue elements at the very bottom of the table all belong in group 3 in period 6. And underneath it, next to radium, Ra, there's a double star box. Look at the very bottom, there's a double star. From Th to Lr, from thorium out to Lr, they all go in there as well. And now that I think about it, this is a mistake too, because we've lost La and we've lost actinium. They belong in there also. Who made this table? But anyway, it's a good idea. They all go into group 3. You get stuff off the internet, you think it's good, then you start talking about it and you realize, oh my goodness gracious, look at this mess. What happened to La and Ac? All right, they belong in those boxes too. All right, cation and anion sizes. Now, we have no charts to decide this. We know how big atoms are. Table S tells us the atomic radius. We have no charts to determine, but we can figure this out. So we're going to look at 52 and 53, sodium and then chlorine. Sodium on the periodic table has a 2-8-111 electrons and 3 orbitals, and that's the configuration. The radius from table S, if we look it up, for both of these atoms, chlorine, are there. Now listen, they both have three orbitals. Sodium's on the left, chlorine's on the right. Chlorine's a lot smaller. Chlorine has more electrons and more protons. Oh, more protons. 3 orbitals, more protons, pulls it tighter. Going across the table, the atoms get smaller because you add more electrons to the same number of orbitals, but more and more positive protons pulls them tighter and tighter. Now, what would be their ion electron configuration? Sodium, being a metal, is going to lose an electron. It's going to become 2-8. The ion orbital, the sodium, is a whole orbital smaller. So the cation, the sodium cation, is noticeably smaller than the sodium atom. It's a whole orbital smaller. It only loses 1 electron, but it loses a whole electron orbital. So now it only has 2 orbitals. It's going to be, cations are much smaller than their atoms. What about chlorine? Chlorine is going to gain an electron. And now this valence orbital, actually with the 8th electron, instead of 7, now it has 8. It's going to all repel apart from each other. It's going to stretch just a little bit more. So anions are all a little bit bigger than their atoms because that extra electron in that outer orbital stretches it out to its maximum size. Cations are way smaller than their atoms. Ions are slightly bigger than their atoms. This is a good example. Now, I just said this. Cations are always much smaller because they lose a whole orbital when they lose their valence electron, or sometimes like with magnesium, aluminum, they lose more than 1. They lose 2 or 3 or how many electrons. Whatever number of electrons they lose a whole orbital. Cations are much smaller than their atoms, and anions are always a bit larger because the extra electrons stretch it out to its maximum size. The electrons are negative. They all repel from each other. They're like, hey, get away from me. And so they all get a little bit larger. Now, what's the group trend for cations, and what's the group trend for anion size? Now, we don't know the numbers. We know the atom size ones. Going down a group, the atoms get bigger because we keep adding orbitals. Going down a group, for any group, the atoms get bigger and bigger and bigger because going down, you're changing periods, and each period is 1 extra orbital bigger. Now, what are the cation electron configurations? Let's do the group 1 metals first. Lithium, 2-1. When it loses an electron, it becomes just an electron orbital with 2 electrons. Sodium, 2-8-1, it becomes 2-8. Potassium, 2-8-8-1, it becomes 2-8-8, loses a whole orbital. And rubidium, which is 2-8-18-8-1, loses that whole extra orbital because it loses 1 electron, becomes 2-8-8-18. 2-8-18-8. Now on the anion side, what about that? Fluorine's 2-7, gains 1 electron, becomes -1. Chlorine's 2-8-7, gains 1 electron, becomes 2-8-8. Bromine gains 1 electron. Iodine gains 1 electron. So here are the electron configurations for the ions, not for the atoms. We in our head, we wrote down the ion configurations. Now, let's look at the metals in group 1 first. The top ion has 1 orbital, then it has 2 orbitals, then 3 orbitals, and 4 orbitals. You get bigger. What about for the anions? You start with 2 orbitals, then you get 3 orbitals, and 4 orbitals, and 5 orbitals. They get bigger and bigger and bigger, right? So what's the group trend for cation size is increasing. Makes perfect sense. Look, there's more orbitals. And the group trend for anion size, they also increase. They get bigger, 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 bigger. This is not necessarily obvious, but if you make a little chart, oh my gosh, how could you get this wrong? Look at the blue ones on the left, the cations. Which has got the smallest atom, the one with the least number of orbitals, which is the biggest. They get bigger going down. The group trend for cation size is increasing. And for the red ones, the anions, you start with 2 orbitals, and you get 3 orbitals, and 4, and 5. Well, which is the smallest one? 2 orbitals, right? And then they get bigger going down the group. The group trend for anion size is increasing. Make a chart, can't get it wrong, right? If you try to do it in your head, you don't really care, like, what the heck's the answer? You might get it right, you might get it wrong. You make a little chart, so easy. Now, groups, you gotta think more, all right? We'll only do 3 at a time here. So we have sodium, magnesium, and aluminum ions. These are all going to make +1, +2, +3 cations. So first we're going to write the electron configurations out, and then we're going to see if we can determine what the trend is. So if we write in these numbers, sodium 281 becomes 2-8, magnesium 282 becomes 28, aluminum 283 becomes 28. Look, they all end up with 28, 28, 28 with 10 electrons. But what else do they end up with? What has sodium got that magnesium ain't got? And what has magnesium got that aluminum ain't got? That's not good English, right? Sodium has only 11 protons. Magnesium has 12 protons. Aluminum has 13 protons. So as we go across the group, just like with atoms, there's more and more protons with the same number of orbitals. And with cations, it's the same exact orbitals, but there's still more and more protons pulled tighter and tighter and tighter. And so the cations are going to get smaller and smaller. 28, 28, 28, they all look the same, right? But if you think about it, with the protons, there's more protons, even more protons, and the most protons in aluminum, they're going to get tighter and tighter and tighter. So the period trend for cation size is decreasing. Now, what about the anions? I picked nitrogen, oxygen, and fluorine, but you know, all the periods are going to work. The electron configurations, what are they? Well, for nitrogen, when it becomes nitride, oxygen is oxide, fluorine is fluoride. Nitrogen is going to gain 3 electrons, oxygen is going to gain 2 electrons, and fluorine is going to gain 1 electron. They all end up 28, 28, 28. They all end up isoelectric to neon. That's what happens. Nitrogen has to gain 3 electrons to do that. Oxygen has to gain 2 electrons to do that. And fluorine has to gain 1 electron to do that. So they all end up with 28. 10 electrons, 2 orbitals. They should be identical orbitals, but look, I have it this time in black ink there. Nitrogen only has 7 protons, and oxygen has 8, and fluorine has 9. With more and more positive protons in the center, there's a greater and greater inward attraction. So what would be the trend for the anion size? They're going to get smaller. For the same reason the cations get smaller, for the same reason the atoms get smaller going across a period. Same orbitals, in this case identical orbitals, more and more protons pulling tighter and tighter and tighter makes them get a little bit smaller. So the period trend for anion size is decreasing. I love that salsa. Now, look at this cool guy. This is a great picture. First of all, he looks like a wackadoo guy, right? He's holding up these big, crazy wooden models of crazy large molecules. In the back, there's all kinds of crazy writing. You're looking up at him because he's an exalted figure. This is Dr. Linus Pauling, who also has a really funny first name, Linus, right? He's the only person to ever get 2 Nobel Prizes by himself. Some other people, they shared the prizes, right? And it's not that they're undeserving. These people are geniuses, but this is the only guy with 2 by himself, so he's the main man, right? Linus Pauling. He came up with this whole idea of electronegativity, which is like my favorite thing. So it's going to be your new favorite thing too. You have to understand this. I'm going to tell you a quick story. So let's say, let's get to the definition, then I'll tell you a story. Electronegativity is defined as the tendency to get an electron in a bonding situation. So let's imagine you and I become friendly. Not friends. We're not going to be friends, right? I'm the teacher. You're the kid. There's no real place for us to be friends, but we can be friendly. And I don't know, it's a crazy day. I invite you to the Skylark Diner for lunch. You did well on a celebration, and we're not even having them this year. But I want to celebrate and take you out to lunch. We go to the Skylark Diner. We both have a cheeseburger deluxe and a Coke or a Diet Coke. And at the end of the meal, I say to you, hey, you want to share dessert? Because I love the dessert. And you're like, all right. So the waitress says, what can I get you? I'm like, I like a piece of cherry pie a la mode, but I like my pie not hot. I want it out of the fridge with vanilla ice cream on it because I don't want the ice cream to melt too much. We're going to share it. So the waitress comes back and she puts the pie between us and she gives you a fork and gives me a fork. And you look at me and you look at the dessert and I smile because I know this is going on. This is like, do you think you should go first? Do you get to eat that first little corner piece? Or maybe you want some of the crust and you think maybe I want the crust, or maybe the ice cream is for you. My mouth is watering. Do you think maybe I want the ice cream first? We're not really sure. And I just smile because I think this is kind of funny. Like, oh, let's see how this works. But finally, you pick up your fork and I pick up my fork. And I smile at you and it kind of lets you like, yeah, go ahead. You go, you get the first bite. So you reach with your fork and I immediately reach out and grab you by the hand and pull your hand aside. And I eat up the whole cherry pie a la mode because it's the best dessert in the world. I love cherry pie a la mode. And it's just a couple of crumbs and a little bit of drip of vanilla. And I push the plate. I'm like, yeah, that's your part. That wouldn't be very nice. I could tell my wife, yeah, I took this really nice kid out to lunch. We both had cheeseburgers and fries and a drink and all. And then we shared dessert. And my wife was like, probably like, good, you didn't eat the whole thing. You eat too much junk. We didn't share that fairly, right? Sharing is a very funny word. Well, as it turns out, when atoms bond together, when they bond in a covalent way, when they share electrons, when nonmetals bond to nonmetals, well, they don't always share the electrons exactly evenly. Some atoms tend to want those electrons more. They have a greater tendency to pull the electrons towards themselves more than other atoms. Sometimes they share nicey nice. Imagine you go out to lunch with your best friend or your twin sister or something, and you share a cherry pie a la mode, right? One of you will cut it, the other one will say, you eat the first bite, one little bite, you get a scale, perfectly shared because you like each other. When we go out, I'm a nice guy, but I have a huge affinity for cherry pie a la mode. I can't share it even. I gotta have it. Some atoms are like me, some atoms are like you and your sister. And there's a way to decide, well, how do these atoms share the electrons? And this becomes much more complicated in a sense, and we'll talk briefly about it, but we'll talk about it more when we get to bonding. When atoms share electrons evenly, when I get the electron half the time and you get the electron half the time because we both have the same desire or tendency to get that electron, we have a bond that's balanced. One side is not more negative more of the time, and one side's not more positive because of where is that electron most of the time. Sometimes when the sharing is perfect, the bond is said to be nonpolar. But with like me and the pie, and I get most of it, almost all of it, I would get all the pie. Some atoms say, give me that electron, I'm keeping it 90% of the time. We can only have it 10% of the time. We're going to share this electron or electrons so that I have a full orbital sometimes and you have a full orbital sometimes, but that sometimes is not 50-50. And what happens in that case is the bond itself becomes a polar bond. The side that gets the electrons becomes a little bit more negative, and the side that doesn't get the electrons is actually a little bit more positive. And that bond polarity leads to all kinds of crazy things, freezing points, melting points, phase changes. There's a lot involved in what happens when bonds become polar. For now, we're just going to decide, is the electronegativity balanced, or how imbalanced is it? And we can measure it using this very simple scale. Now, imagine two hydrogen atoms. Let's look at table S. The first atom, hydrogen, has an electronegativity value of 2.2. And that means, Linus Pauling said, of all the atoms, relatively speaking, I'm going to assign hydrogen to a 2.2. You're hydrogen and I'm hydrogen. We're going to bond. I have one electron, you have one electron. And to bond, we need H2. That means you can lend me an electron and I can have 2 electrons in my little baby orbital sometimes. And then I'll lend you my electron and you get yours back and you can have 2 electrons in your baby orbital and we'll share them. And I want that electron, a 2.2 amount, and you pull also 2.2 amount. Since both of these atoms have the same electronegativity, the difference between yours and mine, 2.2 minus 2.2, is a 0. There's no difference. That means we're sharing these electrons equally. When there's no difference in electronegativity, the bond is said to be balanced or nonpolar, right? Because I get the electrons half the time, you get them half the time. It's a perfect share. I'm negative and positive, you're negative and positive, the same amount. So this becomes what's called a nonpolar bond. And electronegativity, every atom has an electronegativity value. We can compare them. And if it's a difference, that means it's not being shared nicely. And if it's no difference, that means it is shared nicely. In this case, H2, the difference in electronegativity values is 0. This bond is balanced, so this bond is said to be nonpolar. Now, what about this one? HCl. Hydrogen has 1 electron. Chlorine, 287 is the electron configuration. Chlorine says, hey, I only need 1 electron to fill my outer orbital. And hydrogen says, hey, I only need 1 electron to fill my outer orbital. How about I lend you 1 of my electrons so you could feel full, and you lend me back an electron and I can feel full at the same time too. And we'll share our electrons in a covalent bond. Two more nonmetals share electrons. And when we share electrons, we both get that full outer orbital sometimes. It's a good plan. It works out mathematically very well. So look at these beautiful pictures. The hydrogen electron's red, and it lends it to the blue chlorine. And sometimes the blue chlorine electron in the outer orbital jumps over to the hydrogen. Everybody gets a full outer orbital sometimes. But look at the electronegativity values. Hydrogen's we saw is 2.2. Chlorine is down here, 3.2. Now what happens when hydrogen and chlorine bond? Kind of like when you and me eat cherry pie a la mode. I gotta have it. Chlorine has a much higher electronegativity value. That means chlorine has a much higher tendency or desire to get that electron. It's gonna pull it much harder. So what happens is chlorine is gonna get the electron most of the time. Hydrogen's not gonna have that electron most of the time. So in the balance of things, the chlorine side of the bond is gonna be more negative, and the hydrogen side of the bond is gonna be more positive. This bond is pretty polar. It's polar. The difference is 1.0. That's pretty big, right? Now, sometimes hydrogen does get the electrons, 5% of the time. But 95% of the time, chlorine keeps them. So this bond is polar. And ready for this? The whole molecule is just 2 atoms. That means the whole molecule is polar too, because one side's negative and one side's positive most of the time. What do you think that means when a whole bunch of HCl molecules get near each other? All the negative chlorines are going to be attracted to all the neighboring hydrogens to be positive, and all the hydrogens are going to be attracted to the neighboring negative chlorines. All this stuff's going to stick together pretty well compared to atoms like H2 that have nonpolar bonds and they're nonpolar molecules. So this is called a polar bond. Polar bond, polar covalent, because it's not shared, not fairly shared, not shared fairly. Now, we can also draw it like this, H-Cl. We don't have to draw the electrons. We can keep them in our head. HCl can look like this. It's sharing 1 pair of electrons, so we draw a single dash. Now, the arrow up on top is called a dipole arrow, 2-pole arrow. One side's got a positive sign and one side's got the arrow. Now, the positive sign shows which atom or which side of the bond loses the electrons, the side with the lower electronegativity. And the arrow says, look, the electrons are going on that way. That means the chlorine side is going to be negative most of the time. So the bond is polar. And because the molecule is just one bond, it's a polar molecule as well. It's a dipole arrow. Now, the dipole arrow does not replace the bond. The bond is H-Cl. The bond is the dash. The dipole arrow is written on the top or the side or somewhere, the bottom. You got to show it which side of the bond is positive and which side gets the electrons. and it's called a dipole arrow. All right. How fun was that? I love electronegativity. Now, what are the trends? What are the group trends? Let's look at metals and let's look at non-metals, okay? First, we look at the red metals. Got to get table S out. We just got to run these numbers in. Lithium has a 1.0, sodium, potassium, rubidium, and the numbers are clearly getting smaller. Now, they don't change a whole lot. 1.0, 0.9, 0.8. The last two are the same, right? But what is the trend? Trend is, well, they were big on top and they're smaller on the bottom. The trend is they're decreasing. Now, what about in the blue? What about for the non-metals? Look at these numbers. Fluorine's a 4.0, and then it goes down 3.2, 3.0, 2.7. These change much more dramatically, but it's still the top number. At the top of the table is the highest, and then as you go down the group, they get smaller. Going down the group, they get smaller. So say it. The group trend for electronegativity is decreasing. Now, the reason for that, the electrons that you would be adding to the valence orbital to share, it's always further and further away from the nucleus. So even though there's more protons in the atoms near the bottom of the table, the distance from the nucleus makes the inward pull for other atoms weaker and weaker. When the atoms are smaller, there's a greater attraction for, I can't talk to you either. I need to finish my slideshow. Sorry about that. Now, what about going across? Here is period 2, lithium right across to neon. We're going to write all the numbers in right now. Write them in. I'll take a sip of seltzer. Should talk to my wife. All right, look at these numbers. Here's where they are. 1.0, 1.6, 2.0, 2.6, 3.0, 3.4, 4.0 dash. What the heck's going on? I got a whole bunch of things going on. Surely the numbers are increasing going across the period. But what about neon? We're going to get to that in a second. The period trend for electronegativity is obviously increasing. The numbers get bigger and bigger and bigger. And that's the case for every single period. But what's up with neon? Neon has a dash. Well, what's electronegativity mean? Electronegativity, the definition is the tendency to gain electrons in a bond. Neon's a noble gas, doesn't make any bonds, right? It has no tendency to get it, doesn't make bonds, doesn't want to lend you electrons, doesn't want to borrow your electrons, doesn't want to share electrons. Leave me alone, says the noble gas. So there you go. Neon doesn't have an electronegativity value because it doesn't bond. Now, the reason that it increases is the same reason for a lot of things, right? We're going across the period. The same number of electron orbitals, but with more and more protons, it's a greater inward attraction. So as you go across the table, it's a greater tendency to pull electrons to yourself because there's more protons in the middle. Plus, for instance, for the metals here, lithium and beryllium, they tend not to want to gain electrons. They want to lose them anyway. So relatively speaking, going across the table, there's always a greater inward attraction, a pull towards the nucleus because there's more and more protons. But not for neon because neon's perfect. It's already got enough electrons. Doesn't need to, in a sense, gain any electrons to fill up that outer orbital. It is already full. All right, exceptions to the trend. Now, there's always going to be some exceptions, right? There's always some quirky things. Now, the first exception we ever talked about was the staircase business. And I said, if you touch the staircase, if you're an atom that touches the staircase, separates the metals from the non-metals, those elements are called metalloids, like Italian Americans. You're either Italian or you're American, but some people call themselves Italian Americans. You're metal or you're non-metal, but sometimes you call yourself metalloids. But you know what? 9 atoms touch the stairs, but only 7 are metalloids. 2 of them, the dog food, Al for aluminum and Po for polonium, they touch the stairs, but they're metals. They're not metalloids. So that's an exception. So the rule is if you touch the stairs, you're a metalloid, except for 2, Al and Po, aluminum and polonium. So there's going to be some exceptions. There's quirks. It's 118 elements now. They didn't know they were going to get in a table for you and be nicey nice. They're like teenagers, right? Everything's fine until one day they do something really dopey. You wish they didn't do it, but you almost know that teenagers are going to do some dopey stuff. Atoms do some dopey stuff because there's a lot more. This is an intro class. There's a lot more details, the mathematics, the physics, and the number of neutrons. There's a lot of stuff involved in this. we're looking at patterns and trends, but there's going to be exceptions. Now, today, oh look, this is so funny. On my screen, I can see my little picture in the right-hand corner. I don't know where I am on your screen, but my head right now is right on top of that little cartoon drawing. So it looks like I'm a cartoon guy from the neck down, and I'm alive from the, it's like an animation with the really cool. Anyway, this is a funny picture. It doesn't make sense for you. I always wear short pants at school every single day. I don't care how cold it is. But you know what? Today, if I were teaching in school today, I'd have worn pants. And we're like, whoa, Charlie Busso, what are you doing in pants? You never wear pants. Well, I have a few pants. I wear them sometimes, just not to work too often. But what do I do? Every day in September, every day in October, every day in November, every day in December, shorts, 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 every day. But you know what? Today, I was going to wear pants. You know why? It's an exception to the trend. Is it a rule? Do I have to wear shorts? No, I do anything I want. It's my life, right? If I never want to wear shorts again, I got them on right now. But if I never want to wear them again, I don't have to. You expect me to, right? Because I've set up this pattern, right? But today, I wore pants. If you're going to bet, what am I going to wear tomorrow? Shorts or pants, right? You think this is a new me, or is this an exception? So it's an exception. I feel really bad because this is a great slide, because when I'm going to use this slide in my class, normally you're all in school and I wear pants to school and everybody in the whole school is like, what's up with Charlie Busso? I'm breaking the trend. That's all. Nothing big tomorrow, short pants again. So anyway, let's see. What are the atomic masses going across period 4? Now, if we write out all the digits, right, we don't just round them. I guess even if we do round them, right? And if we write out all the digits, manganese, iron, cobalt, nickel, copper, numbers going up, 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 up. What about nickel? Nickel goes down a little. The heck? What's wrong with nickel? An exception to the trend. The pattern is up, 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 with one little glitch in the middle. So what? Don't make a big deal of this. It doesn't destroy the trend. It's an exception. Look at this one. Atomic radius. Atomic radius. That's how big the atoms are, going across from lithium all the way. Starts big, gets smaller, 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 fluorine, and then what? The end gets a little bigger. 2 picometers? I can't even imagine they can measure that difference, really. But it goes up a little. Is that a big deal? Well, there's reasons for it. Reasons that we're not going to talk about. It's an exception. Most noble gases are the smallest atom in the period. Neon? It's a hair bigger. Leave me alone. No big deal. Now, let's look at noble gases, another exception. Electronegativity values. What are the symbols of all the noble gases? You should know these and recognize these, and what are their names? We'll fill them in. Helium, neon, argon, krypton, xenon, radon. No electronegativity values at all because they're noble gases. They have no tendency to gain electrons in a bond. And what the heck's wrong with xenon? Oh my gosh. Xenon has an electronegativity value. What the heck is up with that? Now, as it turns out, when I was in high school, noble gases was said to be inert, I-N-E-R-T, which is a good vocabulary word, completely unreactive. As it turns out, under high pressure, intense conditions, and sometimes needing a catalyst, xenon has been shown to be able to make some bonds because its outer orbital can stretch a little and somehow hold a few more electrons, and atoms can get stuck onto it. They don't normally form, but they can be forced. And then they get somewhat stable and they stick together. How is that possible? A freak. I don't know. It's an exception. Most noble gases have no electronegativity value because they have no tendency to gain electrons because they don't make bonds. Except xenon, sometimes. It's an exception. Don't worry. It's an exception. The table is still really good. It's got some exceptions in it. Now, are there exceptions, for instance, to the net nuclear charge? Think hard. What is net nuclear charge? The net charge of the nucleus of any atom, which includes the sum total of all the protons with a positive sign because the neutrons don't count. No, going across the table, 1 proton is added per box, always, that's how the whole table's set up. And going down a group, there's lots of protons added because they don't get added one at a time going down. You're adding them 8 or 18 at a time. They get much, much more. So that trend is perfect. Now, how about predicting the actual sizes? Predicting, and teenagers hate predicting. They hate like, oh, I don't know. Of course you don't know. There's no right answers. You gotta get approximately right answers. That's all right. Lithium has a 2-1 electron configuration. It happens to have a radius of 32 picometers. It's on table S. I looked it up. When it makes a lithium positive ion, it loses a whole orbital. It only has an electron configuration of 2 because the 1 electron is transferred. So what's the radius? Well, it's got to be smaller. How small? I don't know. 24, about. I didn't look that up. That's my approximation. I made it a little bit smaller. I can do that. You can do that. Magnesium. Magnesium is a mistake. I'm going to fix that right now. What the heck's up with that? Magnesium is 282. Thank you very much. Not 222. The heck was that? It has a radius of 140 picometers. But when it becomes a positive 2 ion, it not only loses 2 electrons, it loses the whole orbital. So what's a whole orbital smaller than 140 picometers? I don't know. What did I say? 125. Seems reasonable. And what about these other elements? Oh, the magnesium, I got to fix it on every box now. Look at this. Pick some numbers. See how they're all a little bit less for the metals because you lose. What about the non-metals? Oh, I shouldn't have gone so fast. Oxygen goes from 2.6 to 2.8.